our last class we were discussing about thread cancellation, that is when we think that a particular thread should not run anymore, then how it can be terminated. So, so cancellation is the process in which we terminate a thread before it is finished. Now, the thread can be cancelled, that is the thread that you want to cancel we will refer to as the target thread. And now, cancellation may be handled in two approaches as we have seen previously. One is asynchronous cancellation. So, it terminates the target thread immediately, and deferred cancellation, in which case the target thread is informed that you should be terminated, and the target thread itself checks periodically that whether there is any message to terminate me, and then accordingly it will terminate. So, the problem with this termination or cancellation is that the resources that are allocated to a thread. So, they also what to do with those resources. So, we have to take a decision on that. So, resources have been allocated to cancel thread, and a thread is cancelled while in the middle of updating the data it is sharing with other threads. So, this type of situation. So, if we try to cancel a thread, so it becomes a problem. So, particularly for the second situation where the thread was updating some data, and where on some, and that data is being shared by other threads as well. So, there actually the difficulty is more, and that is why it is said that we should be the thread should be checking itself that whether there is any cancellation request is there, and if there is any cancellation request, then it will terminate it in a proper fashion. So, that this the data synchronization is not lost across threads. Now, the operating system usually reclaims the system resources from a cancelled thread, but will not reclaim all resources. That is of course desirable, because some resources may be shared across a number of threads. So, if the resource is taken back because a thread is terminating, so that will create problem. So, cancelling a thread asynchronously does not necessarily free a system wide resource that is needed by other threads. So, that policy has to be followed. So, this is the point. In deferred cancellation we have the advantage. So, because the one thread indicates that the target thread has to be cancelled, the cancellation occurs only after the thread has checked a flag to determine whether or not it should be terminated, it should be cancelled. So, there we do not have the problem that these thread resources will be half updated and all that. So, that situation will not occur, because thread will perform the check and it can come to a situation where everything is fine. So, this deferred cancellation is a much better proposition. In case of pthread, so pthread cancellation is initiated by using the function pthread cancel. So, this pthread cancel, so this is this will ask the thread to be cancelled. The identifier of the thread of the target pthread is passed as a parameter. Like in this call, you see that pthread cancel TID. So, here this thread ID is passed. So, from so this TID is has been obtained when the corresponding thread was created. Okay. So, this thread ID is passed here, and this tells that this thread has to be cancelled. Now, pthread, so this is the code for pthread cancellation, and as we have noted in the last class also, like this invoking this pthread cancel, it indicates that only a request to cancel the target thread. So, the thread is not cancelled immediately, just a request is sent to the target thread that there is a cancellation message. So, about the actual cancellation, it will depend on how the target thread is set up to handle the request. Now, pthread supports 3 cancellation modes. Each mode is defined as a state and a type. So, one of them is the off mode. So, this off mode means the state will be disabled, and the type it does not have any meaning there. So, the mode is off, then it will not, it cannot be cancelled. On the other hand, so mode, if the mode is deferred or mode is asynchronous, now there is a question of disabling and enabling the thread cancellation. So, in a deferred mode, if the thread cancellation is enabled, in that case the type of cancellation will be deferred. So, if a thread is created in deferred mode and the current state is disabled, then it will not check for this periodic thread cancellation requests. On the other hand, if it is deferred and the state is enabled, in that case of course, it will be looking periodically for the deferred for the cancellation message, and if the cancellation request comes, then it will cancel at some point. If the mode is asynchronous, again the state can be disabled or enabled. So, the state is disabled, then the thread cannot be cancelled. If the thread is enabled, then the thread will be terminated immediately. So, that is the asynchronous mode of cancellation. So, pthread supports 3 cancellation modes, and each mode is defined as a state and a type. A thread may set its cancellation state and type using an API. If thread has cancellation disabled, cancellation remains pending until thread enables it. So, that is what I was telling. So, if the cancellation is disabled, then no cancellation will take place. A default cancellation type is a deferred cancellation. So, by default the cancellation is deferred, that is good, as we discussed previously. So, deferred has got advantage because this resource sharing and all, so they becomes easy. So, one way of establishing cancellation point is to invoke the pthread test cancel function. So, in a code of a particular thread, so if you put somewhere this pthread test cancel, so it will be checking for this cancellation thread. So, it is like this. Suppose this is the code for the thread, and at some points so suppose it sees that this is a reasonable point at which the thread can release the control, or thread can terminate itself. So, at this point maybe it is the situation where it does not hold any resources with it. So, at this point it can call this test cancel function. So, it can call this test cancel function here. So, it will test whether a thread cancellation request is there or not. Similarly, after some time again maybe at this point it puts another such test cancel function call. So, this way the in between, if there is, when the thread was in this region, so if a cancellation request has come, then the thread will not be terminated immediately, but it will when the next time this test cancel function is executed. So, it will be testing whether the thread is cancelled or not, and accordingly the thread will terminate. So, this way the developer of the thread or the writer of the thread can decide like at which points it can go for this cancellation, and that is up to the programmer. So, this thread programming is expected that the user is quite is a knowledgeable person, then and that fellow can put these cancellation points appropriately in the code. If a cancellation request is found to be pending, a function known as cleanup handler is invoked, and then this function allows any resources a thread may have acquired to be released before the thread is terminated. So, in the test cancel function, while this test cancel is called, so if some resources are held, those resources are to be released, and for that purpose it calls a cleanup handler. So, that will automatically do this resource release and all. On Linux system, thread cancellation is handled through signals, whereas other operating systems they may do it in a different fashion. So, these are the thread cancel function. There is another important issue which is known as thread local storage or TLS. So, thread local storage, it allows each thread to have its own copy of data. So, this is very important because as we have discussed previously, so if there is at the process level you have got code, data and stack segments, and for a set of threads of any process, the code and data, so these two are same. So, these are shared across all the threads, only the stacks are different, stack segments are different, that we have seen. But sometimes it is necessary that thread has got its own data which is not accessible to other threads, and which so that way we can create some thread local storage that will allow the thread to have its own copy of data. So, this is useful when you do not have control over thread creation process. For example, that is when you are using a thread pool. So, maybe from thread pool you are taking some thread and you do not have control over the thread creation process. So, in this case I should have some variable which is used in the thread local storage. So, this is not as local variables, because local variables visible only during single function invocation, but TLS is visible across function invocations. So, it is like this, it is some sort of static data. So, in C language program, so you must have seen this static data type. So, if a variable is defined static, so even within a function 1, so if you have defined a static int static integer x, then across different invocations of this function 1, this the variable x remains live and this x retains the previous value. So, in TLS also, if you define some variable, so they remain active, they remain valid across different invocations of the function. So, as a result, so this is not a local variable, but rather it is a static variable. But of course, it is not visible outside the function, but it is for multiple invocation of the function, the variable is available. So, this is the issue of thread local storage. So, this is another advanced feature that these threads will provide. So, sometimes we need to use them. Another important issue with the threads is the scheduler activation. So, we have got many to many and 2 level models that require communication to maintain the appropriate number of kernel threads allocated to the application. So, scheduler has to schedule those threads and so that this proper execution takes place. They typically uses an intermediate data structure between user and kernel threads, because what happens is that there is a mapping. So, that mapping may not be fixed. Okay. So, particularly the many to many and type of mapping. So, this mapping may not be fixed, and so you have to once at some point of time. So, many to many type of mapping. So, we have got a number of user level threads. Okay. So, they are mapped to again a number of kernel level threads. So, these are the user level threads and these are the kernel level threads. So, they are mapped that way. So, at some point of time, maybe this thread was mapped to this kernel thread, this user thread was mapped to this kernel thread, and sometimes some other time maybe this particular kernel thread may be associated with this user thread. So, as a result, the data, the association between this user level thread and kernel level thread, so that will vary over different invocation or different execution of the system calls. So, we must have some intermediate data structure between this user and kernel level kernel threads, and this data structure is known as lightweight process or LWP. So, this is called the lightweight process. This data structure which has got this data that can be transferred between user and kernel threads. So, it appears to be a virtual processor on which process can schedule user thread to run. So, this data structure, we have got a set of data structures and that way that defines the interface. So, if you are putting one user level thread onto a kernel thread, so essentially you are mapping it onto the data structure. So, this is basically some sort of virtual processor on which process can schedule user thread to run. Each lightweight process is attached to kernel thread. So, each such data structure mapping, so that is attached to a kernel thread. The kernel threads are the ones that the operating system schedules to run on physical processors. So, ultimately these kernel threads will be scheduled onto the onto the physical processors. So, that is how this scheduler operations will take place. So, basically this is the scenario. So, we have got a user level thread. So, that is mapped onto a lightweight process, and from this lightweight process, so there is a kernel thread. So, that will be running. So, this is the lightweight process schema, the way it processes it. So, scheduler activations provide up calls, a communication mechanism from the kernel to the up call handler in the thread library. So, this when this is done, then it will be for transferring the data back to the user thread. So, it will be using this up call, and this communication allows an application to maintain the correct number of kernel threads, because the number of kernel threads is not increased. So, they remain fixed. So, that way we can maintain this order. So, we have discussed about threads, and to summarize the discussion, so thread is a flow of control within a process. Benefits include increased responsiveness to the user, resource sharing, economy and ability to exploit multiprocessor architecture. And threads may be at user level or kernel level, and we can have different types of models, one to one, many to many, etc. So, threads are very useful, as you can understand that threads are required to have this multi-core architecture for exploitation of that thread is very useful. And thread level programming, it also helps because one particular in a client server environment. So, if one client request gets stuck at some point, other client requests can proceed, or in a operating system implementation also, if one process has made a system call and that system call is stuck in the kernel mode. So, it does not happen that other system calls will also get stuck because of this multi-threaded kernel structure. So, they can proceed. So, these are the various advantages, and that is why this thread level programming is very popular, and thread level design of operating system. So, that is also very popular. So, with this we conclude our discussion on threads and all. So, in the next portion, so we will be looking into the CPU scheduling policies, and that will be very important because it will. So, it will be talking about how this CPU is allocated to different processes and threads. So, this is a very important issue because CPU is one of the very important resource that we have, and everybody wants that my job be run on the CPU. So, my job should get attention of the CPU immediately. So, but that is not possible also, because even if you have got multiple CPUs, so at one point of time you can cater to a number of users only. So, it cannot be all the users that are there in the system. So, we do not have so many processors, so that they can be run simultaneously. And there are other issues like there are priorities among the users. Some of the processes are very important, so they should be run immediately. Some processes are not that important, so they have got lower priority. But at the same time, a process has got lower priority does not mean that it will always suffer delay because of this other processes that are there in the system. So, we have to be careful on that line. Then also we have to see like this CPU scheduling policy should be such that every process gets some time for execution, and the system resources that we have. So, they are also getting utilized properly in the way. So, we will be discussing about this CPU scheduling in detail. The concepts that we are going to cover, first we will start with the basics of this CPU scheduling, then the scheduling criteria, scheduling algorithms, and thread scheduling. So, to just recapitulate a bit. So, you remember that whenever a process is available in the memory, so this is in the ready state. So, once the CPU the process gets a chance for execution, so it goes to the running state. Now, in a multi-user or multi-processing system, what happens is that there will be many jobs which are there in the ready state. So, if you represent it in the form of a queue, so you can say that all these jobs, they are waiting in the queue. So, these are different jobs that are waiting in the queue. Now, I have to run a routine which is called scheduler, or sometimes it is called a dispatcher. So, which will be taking up one job from this queue, and it will be putting it into the running state, so that this job that is selected gets chance for execution. Now, one thing you try to understand that this scheduler or dispatcher that we are designing, this scheduler has to be very fast, because even if it takes a very fraction of time, but that is an overhead, because that does not contribute to the system usage. Like we do not say that if the scheduler has for the entire day, if the scheduler has run for say 10 seconds, then also it is not going to add to the system utilization, because this run of the scheduler is not taken as part of the user jobs that are getting completed. So, they are important, the scheduler is very important because I have to schedule these user level jobs. At the same time, they do not come into credit for the system utilization. So, that is how, that is why. So, if you want to maximize CPU utilization, somehow I have to reduce the time that this scheduler takes for execution. So, we have got these ready processes that are there in the memory, and they are to be put onto the running process, running state for execution. So, how do we do this? So, that is the overall thing that we are going to learn in this particular portion of the discussion. So, So, objective that we have is to introduce CPU scheduling, which is the basis for multi-programmed operating systems. So, if you have got a single user system and the user is just firing one job and there is nothing else to do, then of course, the scheduler is not necessary, because the scheduler has got only one thing to do and that can be done very easily. So, we do not have to depend on, we do not have to make a choice like which job to run next. So, only one job will be running and that will be running always, and when that is over, then the CPU will remain idle until and unless the user gives another job for execution. So, that is the first point, is that for multi-programmed operating systems. So, we have got this CPU scheduling problem. We have to describe various CPU scheduling algorithms. So, the different algorithms have been proposed. One thing that we want, that I would like to mention, is that the CPU scheduling algorithms that we have here, they must be very simple. Okay. So, because if it is a complex logic, then their execution will take more time. So, that will add to the overhead of the system, so this CPU scheduling algorithms, they must be very simple compared to the other scheduler that you may possibly remember, the long term schedulers, which were selecting the jobs to be submitted to the system. So, that way it was choosy, because that long term scheduler was trying to optimize utilization of all the system resources. So, it was trying to make a job mix such that all the system resources are utilized properly, but that is done not that frequently. So, we can be choosy there, but this CPU scheduling algorithm, so they are not that, they cannot be that much choosy, they have to do it very fast. Now, to discuss, we will discuss about the evaluation criteria for selecting a CPU scheduling algorithm for a particular system. Like different algorithms, they will have different properties, and the some criteria, the evaluation criteria that you want to optimize. So, based on that, we may like to choose one CPU scheduling policy or the other on the particular system. We will be looking into the scheduling algorithms of some operating systems. Now, to start with, we look into the structure of any process. Okay. So, any process, so it will be doing something like this. So, to start with, it will be doing some, it will be, so any program that it starts, so it gets the chance for execution in the CPU. So, it is, so if you look into this look into any program, after it starts executing, then most probably it will after doing some basic initialization of variables and all. So, it will be asking for some user input, like say maybe if I am finding the roots of a quadratic equation, ax square plus bx plus c equal to 0. So, this equation, then there may be some initialization of some of the temporary variables. After that, it will take the inputs a, b, c from the user. So, when it is doing this, so this is an IO operation, whereas the initialization that it was doing before this, so that is some CPU operation, because memory location initialization. So, for that we will have instructions, and those instructions are executed. So, they are load, store, add, store, read from file, etc. So, they are the so this load, store, add, store is fine. So, this is these instructions are accessing memory and all, but as soon as it comes to a instruction like read from file. So, in this particular case, input ABC, the ABC may be coming from a file or ABC may be coming from keyboard, but now the program cannot proceed further. So, it will be stalled here until and unless this IO operation is over. So, it is waiting for the IO to be over, and once the IO is over, then it will again go into computation. So, again it does say 2 steps of computation, then again it will be doing some IO. Like here, after getting ABC, so it may be calculating the discriminant b square minus 4ac and all that. It will be calculating the roots R1 and R2. So, up to that much is fine. So, after that it goes into printing the roots. So, print R1 R2. So, as soon as it goes to the print statement, again it has to wait for the IO operation. So, this wait to write to file. So, it is equivalent to write to IO device. So, it is trying to it is trying to write something onto the output device. So, again it has to wait for IO. So, this is a small program. So, after printing this, so this terminates, but what in general what can happen is that this alternation of CPU operation and IO operation can go on for quite some time till the program terminates. So, that is how this is going to happen. So, any program execution you can divide it into a number of sections. So, one part is for doing the CPU operation and the next part is for the IO operation. Again the next part is the CPU operation followed by an IO operation, like that. So, these are called CPU burst and IO burst. So, CPU burst is the range of program execution when it is doing some CPU operation. The CPU is actually needed for doing those operations. So, all the computations that we have, so they are part of the CPU burst. And then for the IO operation, so it has to go to an IO burst. Now, depending upon the program that you have in your hand, the sizes of the CPU burst and IO burst may vary. Like if you have got a database type of application, then you see that most of the time it will be trying to read the records from the database. So, as a result it is more of IO operation than the CPU operation. On the other hand, if it is doing some signal processing algorithm is being executed, so at the beginning it reads the values of the signal samples and then it goes into computation, and as a result the CPU burst is large and possibly it will do very little amount of IO operation. So, that way the size of CPU burst and IO burst, so they will vary for different processes. And we have got this CPU and IO burst cycle. So, process execution consists of a cycle of CPU execution and an IO wait operation, and CPU burst distribution is a main CPU, that is the main concern, because IO anyway if the processor, if the program is waiting for some IO operation to be done, then it does not matter, because in that time CPU can pick up some other job and it can do that. So, this type of IO burst size does not affect this CPU scheduling anyway, but what is going to happen is the size of the CPU burst. So, if the CPU burst is very large, then I can have different types of policies. One policy may be that I give the CPU for this entire time to the process. So, a process is given a CPU and only when it finishes the current CPU burst and goes into the next IO burst, then only the CPU is taken back from the process. So, this is one type of situation, but that way some other process that has arrived may be waiting, and particularly the CPU burst is large, then we have got this problem. So, another policy may be, okay, I give some give the CPU to the process, but after some time I take it back since it is taking too long time. So, that is another type of. So, this way you can think about different policies. Okay. So, in this portion of discussion, so we will be talking about what can be the different policies, so that based on this CPU burst size we can take a decision possibly, and we can come up with a policy so that this CPU utilization is maximized. So, this is the basic idea. So, what we want to do is to maximize this CPU utilization. So, this is the point that we want to highlight. So, we will always try to utilize CPU and what is the ideal value for this CPU utilization? So, that is definitely 100%. We want to make CPU utilization 100%, but that is not possible, as we will see, because there will be many other things to do. So, utilization will not touch 100%, but we will try to do that.